And they were basically sensors that connected over USB. And there's something kind of nice about that, because like you want to program something on your computer with like processing or Python, and you want to use your computer but connect to hardware. And that's like, an Arduino can you do that, but then you have to do this like serial port communication thing. So some of the boards that we've sold that are really popular are the FT232H and MCP2221 modules. And these are chips that are basically USB to hardware conversion. And you have like a special driver from FTDI. And, you know, I don't have an FTDI board here, but basically, you know, you have USB commands in, and there's like a couple GPIO, and you can do I2C and SPI and UART. But the problem is that these chips are like fixed, right? They can only have certain functionality. And what's neat is with the RP2040, you can use this firmware called U2IF. So let's go back to my computer and I'll show this off. Because this is really one of the cool things about Raspberry Pi is this person, execuc, I don't know, whatever. I don't know how to pronounce it. 2 years ago, right, they made this firmware called U2IF, and what it does is it takes USB and over HID and turns into I2C, SPI, and other capabilities. And what's neat about that is that means that you can, on your desktop computer, write C Python code that then runs on hardware remotely, like over USB is the transport. And it actually works really, really well. So it's like, you know, they even said, hey, by the way, like you can use this with Blinka. And we do have this working with Blinka for I2C, SPI, and PWM and Signal. And you can see they added like more stuff like, you know, NeoPixel, stuff that the FT232, like in the MCP221, don't support, or I2S. So some of these more advanced protocols are supported. So what that means is, for example, here's my little desktop window, and I'm in my, it says MicroPython, but it's my CircuitPython libraries. It's just folder hasn't been renamed. And I'm in the example, sorry, this is, I pasted this thing. I'm in this folder where I have all my examples for, my examples for driving the e-ink display either from a CircuitPython board or from a Raspberry Pi computer. But now for my CPython board, I can run what would be like a Blinka with Pillow, which is a graphical system in CPython firmware, and I can take advantage of all the power of my computer, and I can use it to drive the e-ink display. So on the overhead, maybe you can flip right back. So this code is running, the code that's drawing these graphics on the e-ink is running on my computer, sending SPI and GPIO data through U2IF that's running on the RP2040. It's just a firmware blob that I've programmed onto here. And it's drawing to the e-ink display. So, you know, what could this be used for? Well, let's say I want to have an e-ink display and I want to have it have a lot of complicated data that needs OAuth, that needs password, that needs, you know, computer computation. But how else would you connect an e-ink display instead of like having some sort of like weird protocol between the RP2040 and like the COM port, and it's like trying to send messages back and forth? I'm just controlling the e-ink just directly, and Blinka transparently thinks of it as like, oh, your computer has SPI and I2C and GPIO hardware. And so this is like one example. So, you know, let's say I could make a little desktop display, again, connect to my computer, but you can take it a little bit farther than that. Like, for example, you could have it, U2IF running on this RFM Feather, and now I can connect to sensor nodes and collect the data on my computer, you know, store it to an MySQL library, send it to some online service, interface it with my email or social media, ditto with the CAN bus Feather. So, you know, having a USB to CAN bus interface is now like really easy. I run U2IF on this RP2040 and then use SPI and GPIO to communicate with the MCP2515 SPI CAN bus chip. So this definitely like solves a problem that I think I've seen people have, where they're like, I want to have sensor data in or out on my computer but I need something that can do more than the FT232H. So we will compile the U2IF firmware for all these different chipsets, and so that's kind of neat. So some of the things I'm going through and testing is just, Liz made the firmware file, and then I'm just, going through and verifying it, and then she might do a cool project with this, and we can also port some other libraries. Another thing is, I want to show, like, there's another, I can go back to my computer. Dan Halbert, who works on CircuitPython, was like, oh, you're doing all these Bones boards. Can you make a board that is, makes it easy for people to do, like, prop maker projects? Because we have the prop maker feather wing, and people often plug that into an RP2040, but there's still, like, soldering required. And basically what Dan was asking, is there a solder-free way that we can have people make battery-powered prop projects that have audio and NeoPixel and maybe even servos? So this is the RP2040 Bones board, and then over here I have a LIST 3DH accelerometer, so it's like motion and activity it can detect. This is a 5-volt level shifter for the NeoPixel output. And this is a Max 98357 I2S amplifier. So the RP2040 doesn't have a DAC, but it does have pretty good I2S support through PIO. So you can have, like, really, in CircuitPython, it plays audio great. You can play MP3 files even over I2S. The audio quality is going to be really good. So we have a Class D speaker output and then one button input. So this is going to be a terminal block. It's not rendering, obviously, here, but it's a screw type terminal block that's 0.1 inch spacing. And then there's also going to be a little spot you can plug in a servo. So you can do, like, pretty advanced projects here. You got, like, motion, sensing, robotics, NeoPixels, and audio, and then, one button. So if you want to have, like, a activity. And then, if you need more stuff, of course, you have the full feather pinout. So that's another design. So I finished this one. Sorry, this one got finished this week. And then I'm kind of designing a couple more RP2040 feathers, but I have to finish the ones I've already started. I've got, like, you can see there's, like, a ton here that I've already begun. So I gotta keep moving on. All right, so I have one more thing. Just checking the time. I'm doing good. So the last thing is that I wanted to make something like the Scorpio, right? But instead of 8 I pins, maybe it would drive, like, 1 or 2 NeoPixels. But the idea was that it would have, screw terminals, you can have NeoPixel out, and you can get 5 volts, 3 amps from USB-C. But it is possible to get 5 amps. And 5 amps would basically be, like, just a massive number of pixels. And then you could plug this into a really big USB-C power bank, like for a laptop, a power adapter, and get 5 amps out. I'd probably have to make this a 4-layer board just to be able to get that current over to the other side of the board very efficiently. But to do that, I think I need to use a USB Type-C power delivery chip. And so I'm started to develop a breakout board for that would negotiate the USB power delivery spec. Now, I think that you can do it with just PIO on the RP2040, but some of these chips are so inexpensive. It's like, instead of, like, having to, like, deal with this protocol that's, like, another layer of complexity, the FUSB 302 shown here is a chip that connects to the CC pins on your USB Type-C. So these CC1, CC2, those are the pins over here. Those are, like, the extra pins that you would connect a 5K pull-down resistor. But instead of that, they're connected to this chip, and this chip can communicate over I2C. And then, if you don't send it any commands or requests, I think it just does 5 volts, 1 or 2 amps as usual. But you can communicate with this chip over I2C and say, hey, I want you to negotiate for me and get me a higher voltage, or a higher current or higher voltage, or check what current is available. And then the USB-C power adapter communicates back and says, okay, I can give you max 3 amps. I can give you max 2 amps. Maybe you even want to boost the voltage up to 12 volts for some reason. So this chip does that job. So I wanted to start with just a breakout for that. And that's what this is. Let's go to common. Let's turn off the back. So this has a USB Type-C plug here connected to the USB 302. The data lines go out here. So if you want to if you want to still get those data lines for connecting to your microcontroller, that's fine. And then it would negotiate VBus, and this VBus could be anywhere from 5 to 20 volts. But there's one thing that I had to spec today, which was if you're going to use this chip, it needs 3 volts for the power and for the chip itself power. And it doesn't have a built-in regulator. So instead, you have to get a regulator that will able to handle VBus going up to 20 volts, because normally USB is 5 volts, but in this case, it can go up to 20. And so the great search this week is going to be, this is a little bit cheap. This is one part that's valid, but how to spec a low dropout regulator that can handle 20 plus volts and gives you 3.3 volts out.
Yes.
So let's do it.
All right, ready?
Yes.
Here we go.
Where in the world is that part I need? The Great Search with Digikey.
The Great Search, brought to you by Digikey and Adafruit. Every single week, Ladyada uses our power of engineering to help you find the things that you're looking for on digikey.com. Ladyada, what is the Great Search of the week this week?
Okay, so this week I'm working on this power delivery chip, which would negotiate with a USB wall adapter. And I have one here, for example. And this wall adapter, this is USB Type A. I had a USB Type C. Oh, it's over there. Hold on 1 second. I'll get one.
Okay.
1 second. I'm not going anywhere.
Breaking the fourth wall.
Yeah, but
Fifth
wall. People understand I have legs. I get up once in a while. Okay.
Yeah, it's not like the Facebook virtual world where the characters didn't have legs.
Okay, so this is a USB adapter with USB-C on it. And then let's go to the overhead real fast. And I'll just show the text so people can see it. Okay, so this, I'll autofocus on it. Okay, so you can see here, this has multiple outputs possible. So, there's only one plug, but it can give you 5 volts, 3 amps, up to 20 volts, 3.5 amps. And when you connect normally, if you don't do anything special, it'll give you 5 volts and be like, hey, you got 5 volts and be happy with that. But there could be some cases where you have motors or big battery packs or something you want to negotiate and get higher voltages, maybe up to 20 volts. That's the maximum that you can get from USB Type-C. And to do that, the device on the other, see, this says PD, power delivery. The device on the other side has to negotiate. It has to request that higher voltage. And it isn't as simple as just setting a couple of resistors. It actually has to do this bidirectional communication where it sends data back and forth to say, hey, what voltage can you supply and how much current and how much do I need and this is what I want. And it's non-trivial, right? So to do that, we're going to use a helper chip. So let's go to the computer. And the helper chip I'm using right now is the USB 302. There's actually a couple different chips that do this. But this is the one I picked. It's low cost. It communicates over I2C. It's available on digikey.com for 60 cents, and we'll show that. And what it will do is that this VBus, when you first turn it on, it'll be 5 volts, but then you can communicate over the CC lines. And this chip is going to say, negotiate up to 20 volts. When it goes up to 20 volts, I still need this regulator here that provides 3.3 volts to work. This needs to work no matter what. I don't need a lot of current, maybe only 10, 20 milliamps. But I do want to be able to have it function and not blow up, even if it goes up to 20 volts. And I want a little bit of headroom above that too, right? Because you can sometimes get 21 volts out of the USB PD, and then maybe there's a little bit of spikiness. And so let's say 24 volts, right? Just to give ourselves a 20% engineering margin. I need to spec a regulator that can give me this. So let's go to Digikey. And first off, I'll show you the USB 302. That's the chip I'm using. Yeah, so this is, sorry, this particular one isn't in stock, but yeah, this one is in stock. So there's a whole bunch in the family, Type-C controllers. They're fairly inexpensive. They're like 50, 60 cents, which is a great deal. So you just like plop it on. It's not even very big, connected to the CC lines. And over I2C, you have, there's little drivers that are published everywhere for various platforms. Tell it what you want. But like I said, it doesn't have a built-in regulator as far as I can tell. You need to connect an external 3-volt regulator that can run off of the USB no matter what. So let's find a 3.3 volts LDO. And so the question is, why am I using an LDO, not a buck converter? Mostly because I'm cheap and I don't need a lot of current. A buck converter would totally do a great job here, but it's going to take up more space. It's going to cost more because I'm going to need a diode and I'm going to need an inductor. And I don't need that much current. I'm pretty happy with a very simple LDO that costs, maybe 10, 20 cents. It does the job, and then, I can always redesign this later if I need more current, which would necessitate a buck converter because the power dissipation would be too high, especially if I'm requesting 20 volts or 15 volts. All right, so voltage regulators, and there's a lot. I've already kind of pared it down because I said 3.3 volts, but let's just go to the plain regulator. So if I don't specify 3.3 volts, there's 70,000 regulators. Digikey has a lot of stuff in stock. So let's look at active. Let's look at ones that only have positive output, one regulator, and fixed output type. And I also want it to be in stock. So that'll get me down to about 10,000 pieces. Next up, the voltage output, I want it to be fixed. If I was willing to go with a adjustable, I set it with a resistor divider, there'd be more options, but frankly, there's a lot of options already. I don't think I need, it turned out I found so many that I was like, you know what, why have 2 resistors if I don't need them? So many LDOs have 3.3 volts output. All right, so now I have 1,700 options. Next up, I don't care about the dropout so much because, again, I need a lot of current. For current output, I did want at least 100 milliamps. I don't think I'm going to be able to get 7 amps, but, I'll go all the way up there just to be complete. I do want it to be surface mount, not through hole. I don't want a TO22 or whatever. And the voltage input. Now remember, the tough part about this, not the tough part, but the challenge, is that this V-bus, which nominally would have been 5 volts, now can be up to 20 volts. And so I need to make sure that my regulator can handle it. So I can't pick anything too low. There is 20, but again, 20 is really cutting it close. You want to give yourself a little bit of margin. So let's give ourselves up to 24 volts. I don't think 120 is going to give you anything. But for completeness, I'm going to select everything above 24. Okay, so now I've got 300 options. Let's look at some of what we got here. So lots and lots of options. This is a very common issue. One of the things that you'll have to decide is the trade-off between packaging and power dissipation. So in general, the bigger the package, the better your power dissipation. You'll have to calculate if you have 20 volts. If you have 20 volts of output and you are doing 3.3 volts, that's 16 volts difference. And then let's say you're drawing 20 milliamps. So it's a third of a watt. If you're driving, because the voltage difference times the amount of current, that's how much heat you're dissipating. For this design, I think I'm going to just warn people, hey, like you're not going to get, I don't need more than 5 to 10 milliamps to drive the chip itself. But if you want to use that for other circuitry, you may not, and you've got the 20 volts output, people have to kind of realize, like, hey, I'm not going to be able to get that much current out of it. I think that's fine as long as I document it. I'm going to still stick with going with a SOT 23.5. Although, I think I might do some more math and verify I don't need a SOT 89. A SOT 89 is it's a little bit bigger, but it has a very good, you see that big tab. It's a nice big heat sinking tab. That said, I think if you see, or you could go with this, a HT SOP 8 with a big power pad on the bottom. So, again, calculate how much current you're going to need. You need a lot of current. This TO225 will dissipate like a watt or more. But let's go with the SOT 23 size. So go over here. And I'm going to skip the SOT 89. Let's do the SOT 23. I'm going to do the 5-pin version, which I kind of like because it has an enable pin. And it's also kind of a well-known version, although, well, maybe I'll select these as well. You never know. And then SC74, that's the smaller version. Well, I'll select also. Okay, so now I've really got not that many options, but if you don't need an enable pin, 3-pin version will work fine. I tend to like having an enable pin. I don't know why. This is kind of funky. It's like a caterpillar of some sort. 8-pin SOT. Don't you see a lot of those? All right, so a lot of good options. I don't really care about quiescent current. That's something that if you want, you can care about. Voltage max, again, I don't think I need the higher levels, but let's look at, there's quantity available and pricing, and I kind of like to do a balance between the two. Some really good options here: 36 volt, 24 volt, fairly good dropout. All these have good current capabilities. The RT90 series, GPS 7933, all of them are good price, also about 50 cents or less. But I was actually kind of into this MCP 718 BSN. I'll tell you why. Given that there's like a bazillion options, there was like 30 options available and more if I was willing to go with a different package. This one, if you have 5 to 9 volts, it will give you 300 milliamps out. So at a lower, as long as you're within the power capabilities of this package, you can get 300 milliamps, which is kind of nice. So if you're happy to negotiate, again, maybe you're negotiating only 5 volts, but you want, 5 amps. The dropout's small enough that this 300 milliamp drive won't, dissipate too much heat. The price was really nice. It was only 25 cents. What a good deal. And then, looking at the data sheet, this used the standard pinout. And there was actually one of the chips that I found there didn't have the standard 5-pin SOT 23 5-pinout. And it was stable with ceramic capacitors, which is something to watch for. Sometimes they're not. It had thermal shutdown and current limit protection. So again, if people tried to overdrive drive it at high voltages, it would be fine. And I've always had really good luck with the onsemi voltage regulators. Also very low quiescent, which is kind of nice. So altogether, a pretty nice little regulator. So this is my pick, MCP 718. That's what I'm going to use.
That's a great charge.
Where in the world is that part I need? The great search with Digikey.
Okay,
That
we
is
did
our
it.
show. Thanks for joining us. Have a fantastic week that's coming up ahead. We have a ton of stuff and more. We will see everybody later.
Thanks, everybody. Have a great Easter.
That's Ladyada.